Jesus Christ. The DSA exam's tomorrow, and I don't know the Hungarian algorithm. I have an idea. Aha! Found it. Okay. Ancient Demon Scroll. The following incantation is for summoning Stampus, the archdemon of algorithms. Blah 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 crystals, blah 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 pentagrams, blah 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 candle. Wicked. Okay, crystals, pentagram, candle. Hoc nocte animam miam ut pranderet.
I am Stampus, the archdemon of algorithms. Why have you summoned me, mortal?
Oh, beast of beyond, help me with this pesky Hungarian algorithm.
Very well, but for the small price of your soul.
Okay.
Here is the contract. Sign here.
Done.
Let us begin. The Hungarian algorithm is used for solving the assignment problem. The assignment problem is finding a minimum matching in a bipartite graph. Imagine you have a number of agents and a number of tasks. Each agent could perform each task for a particular cost. You want each agent to perform a single unique task and minimize the total cost. This is known as an optimum assignment. The Hungarian algorithm takes an n by n cost matrix as its input and works out an optimum assignment. Here is the pseudocode. Step 1. We just subtract the minimum of each row from every value in that row. Step 2. We do the same for the columns. Step 3. Draw lines over all the zeros using the minimum number of lines. Step 4. If the minimum number of lines is equal to n, the dimension of your matrix, you're finished and have found the optimum assignment. Pick a different zero for each agent. These are the correct agent task pairs. If the number of lines is less than n, go on to step 5. Step 5. Subtract the smallest entry, which is not covered by a line, from all the values not covered by a line, and add it to the values that are covered by 2 lines. Return to step 3. In this video, I'll be using an extra column and an extra row to keep track of the minimum costs for rows and columns. You don't have to use these, but I like to because I think it makes the algorithm easier to think about. Consider this problem. 4 of your friends are into making their own drinks. They all make beer, cider, spirits, and some sort of soft drink. You'd like to buy one of each type, but you want to spend the minimum amount of money possible because you're a tightwad. This is a perfect candidate for the Hungarian algorithm. Consider Anthony on the top row. No matter what drink he buys, he will have to pay a minimum of £1. We subtract 1 from all the values on that row and put 1 in the column on the right. The numbers in the row now represent how much more than the minimum Anthony has to pay for each drink. Repeat this now for all rows. Now we must attempt to do the same for the columns. Subtract the minimum value in each column from each value in the column. For most of these it's just 0, so they'll remain unchanged. The next step is to cover all the zeros in the matrix with the minimum number of lines. Here, we can cover all of them using 3 lines. When you are drawing your lines, ignore the excess column and the excess row. For this problem, n is equal to 4, so the number of lines is not yet equal to n, so there's still work to do. Now we have to look for the smallest number which isn't currently covered by a line. As you can see, it is 1 in Anthony's row. Subtract it from all the values in the matrix which are not covered by a line. Remember not to think of the excess row and column on the bottom and the right hand side when you are doing this, as they merely represent the minimum cost incurred for each agent and task. For each row that you subtracted values in, add the value once to the excess column on the right, as now the values in the rows which represent the cost above minimum have decreased. The value for the minimum must increase. You also need to add the smallest value to cells which are covered by 2 lines. Here there are 2, one in Beth's row and one in Chris's row. Because you have added to these, you must subtract the value once from the excess row at the bottom, giving it a value of -1. We have completed step 5. We must go back to step 3 and execute it again. Now we can cover all the zeros in the matrix with 4 lines. Because n is 4 in this problem, we know we have finished. If the number of lines was less than 4, we would have to continue executing step 4, 5, and then 3 until it was equivalent to n. To find the optimum assignment, choose the tasks with a value of 0 such that each agent has a different task. To find the total cost, you can add up all the values in the excess row and the excess column, giving us a value of 7, as these represent the minimum cost for that particular assignment, and seeing as the cost of all these cells is now 0, the minimum is equal to the total cost for this assignment. You can also work out the total cost by just looking up the costs of these agent-task pairings in the original unchanged matrix. Now we have found the minimum matching for this matrix.
But what if I need to maximize rather than minimize?
Good question. If you want to maximize instead of minimize, you need to change your table slightly. Maximizing the cost that you pay is the same as minimizing the cost that you didn't pay. So if we change all the cells in the matrix to now represent how much less that cell is than the maximum possible cost of a drink, we can then run the Hungarian algorithm as normal to find a minimum in this new matrix, which will tell us what the maximum assignment is in the original matrix. So find the max value in the matrix and then go through the matrix, changing every value to be the max value minus that value. So for the max value, you'll just get 0. Then run the Hungarian algorithm as normal. To find the max cost, you can add up these agent-task pairings in the original matrix, or you could do n times the maximum value minus the total values in the excess row and column, which here is 40 minus 9, which is 31 maximum cost.
And what happens if I have more tasks than agents?
The Hungarian algorithm only takes an n by n cost matrix as its input. If you have more tasks than agents, you need to reformat your matrix so it's n by n. Add a dummy row where all the values are the maximum value in the cost matrix. Then execute the algorithm as normal.
And what happens if I have more agents than tasks?
If you have more agents than tasks, you need to insert a dummy column on the right and fill it with the maximum value in the matrix. Then execute the Hungarian algorithm as normal.
And what is the time complexity of this algorithm?
The complexity of this algorithm is O of n to the 4th.
Well, there you have it. The Hungarian algorithm.
Thanks, Stampers. Now I'm going to pass my exam.
Well, I must be going now. Back to the infernal plane. Farewell.
See you later.